Hi guys, this is the team consisting of Arshdeep and Shresh presenting the linear algebra project for the course EE5120. So the paper we've selected revolves around the use of linear algebra, specifically the use of Markov chains and transition matrices to construct a linear model to model the economic growth and the change in economic distribution along time. So before we go into how the model is built and the flaws of the model and how we overcome those flaws, we'll briefly gloss over the concepts of linear algebra used in this. So the first and foremost, Markov chains. So Markov chain is a stochastic model used to describe a sequence of events in which the probability of each event depends only on the state attained in the previous event, as in the current state depends only on the previous state and not on the states preceding it. Another important concept related to Markov chains is a transition matrix. So transition matrix basically represents the transition dynamics or the probability of the occurrence of the next states given the current states. Important properties of transition matrices are that the sum of the columns of a transition matrix is always 1, and since each of the entries is a transition probability, they obviously lie between 0 and 1. And here's an example of a 2 by 2 transition matrix. So now finally coming to our linear model to model the transition dynamics between the economic distribution across different time periods. So the economic distribution at a given time period is represented by a stochastic state vector. The stochastic state vector of n dimensions contains n different values which sum to 1, and each different value represents the proportion of countries living in a particular economic condition. Similarly, the transition matrix is a Markov matrix which will be used to determine the transition of the economic distribution state vector from one time to another. So the equation obtained is t into Pn minus 1 is equal to Pn. So another important concept used in this analysis is the concept of eigenvectors and eigenvalues. So first of all, we'll describe what the steady state of a transition matrix is, and then how we use eigenvalues to calculate the steady state. So any vector S for a given transition matrix T such that T into S is equal to S again is called a steady state. This is because once this vector is achieved, irrespective of how many times you multiply the transition matrix to it, will still remain in the state S. Another way of looking at this is that S is an eigenvector of the transition matrix with an eigenvalue of 1. So in a manner of speaking, to determine the steady state of the transition matrix, all we need to do is find the eigenvector corresponding to the eigenvalue of 1. Next, we'll go over the proof that for any given transition matrix, there will exist a vector S for corresponding to the eigenvalue 1. That is, the steady state of any transition matrix will exist. So to now going over the proof, to find the eigenvalues and eigenvectors, we write the characteristic polynomial which is given by the determinant of t minus lambda I is equal to 0. And now we're obviously interested in the eigenvector corresponding to the eigenvalue of 1. So substituting lambda is equal to 1, we get determinant of t minus I is equal to 0. Now, as we previously noted that the sum of each column in a transition matrix is 0. And by subtracting the identity matrix, we're subtracting exactly 1 from each of the columns. So evidently, the sum of each of the columns of t minus I will become 0. This implies that T minus I is a matrix which is not linearly independent, or it's not a full rank matrix. Hence, its determinant will always be 0, thus implying that the transition matrix always has an eigenvector corresponding to the eigenvalue of 1. Hence, a steady state is possible for all transition matrices. Now that we've covered all the mathematical concepts, we'll delve into how we determine the transition matrix and state vectors and study their evolution over time. So using empirical data, we divided the countries into 3 categories. The countries whose GDP per capita as compared to US was greater than zero point 0.4 were in the high bracket. as in the prosperous countries, the countries whose GDP per capita as compared to US was between zero point 0.1 to zero point 0.4 were in the middle bracket, and the ones which had less than zero point 0.1 GDP per capita as compared to US were put in the poor bracket. So, and then using stochastic data, and then using data, the state space vectors for 1980 and 2000 were found. And then by comparing the evolution of individual countries, the transition matrix was determined, and we can see all the three values. So now we calculate, as mentioned before, we calculated the steady state of the transition matrix by calculating the eigenvector corresponding to the eigenvalue of 1, and as evident in this equation, the vector obtained was this. And if we normalize that vector, we'll get the state space vector representing the economic distribution, so which is this vector. And using the same transition matrix, we can also study the evolution or the division of economy across the intervals of 20 years. So we've also calculated the values for 2020 and 2040. Now, this result was particularly discouraging for the economists at the time, because it clearly states that the world economy in the near future will be twin peaked or divided between rich and poor countries, and there will be an economic divide which is very unstable for the modern world. So further analysis into the model showed that there were fundamental flaws in the model, and the world economy will not actually diverge into twin peaks but will converge to a singular high peak. So now we'll gloss over the flaws in the existing linear model and how we can correct that. So the two fundamental flaws were that the model assumed that the world population is constant, which is obviously false, as the population is dynamic and is constantly increasing and will reach a steady state in the near future. And another assumption was that there is no interaction between the different sections of the economy, which is again not true. As one section of the economy grows, then the other sections of the economy grow as well, and migration do occur between these countries. And the third and the most fundamental flaw was that because of all these assumptions, the transition matrix won't remain steady. As in, for each different time period, like from 1980 to 2000, and then from 2000 to 2020, the transition matrix will change, and we need a model to account for that. In the subsequent slides, we'll prove why the transition matrix is dynamic and how we can come up with a model to account for this dynamism. So as I mentioned before, like, the transition matrix is dynamic, and the approach that it is static and will remain same for the different time periods is flawed, and we need to come up with a model for matrix evolution to account for this dynamics. So another study was conducted to account for this new dynamic matrix, in which the countries were divided into 6 sections this time, just for more precision, and the parameter for division was still the same. Countries that were whose GDP per capita as compared to US was more than 0.8 were tier 1, and as evident from the graph, and for those who it was less than 0.05 were put in tier 6. And then this study was conducted in 2010, and we had the capability of calculating the transition matrix for two different time periods, that is from 1970 to 1990 and from 1990 to 2010 by the previous mentioned method. So if we calculate the transition matrix from 1970 to 1990 by comparing the transition of individual countries between 1970 and 1990, then we get the following normalized transition matrix. And if using the same matrix we calculate the evolution, like we calculate this matrix from 1970 to 1990 data, and if we apply the same matrix, assuming it will remain constant from the 1990 to 2010 period, and calculate the projected proportion of countries in different sections of the economy in 2010 and compare it with the actual data, we see that there is quite a significant divergence in the two values, as evident in table 2, that the model, this linear model predicts that only 27 countries will be in tier 6, whereas 16 countries will belong to tier 1, which is clearly false, as objective data from 2010 shows that around 27 countries will actually be in tier 6 and 16 countries will be in tier 1, as compared to the model's projection, which predicted that 37 countries will be in tier 6 and 3 countries will be in tier 1. So the actual disparity between tier 1 and tier 6 is much less than predicted by the model. So it appears that there is a much more upward movement in the steady state or constant state that M1 can explain. And the answer to the stability question is obviously that M is dynamic and not a stable matrix. And so if we calculate using objective data again the transition matrix from 1990 to 2010 period, we see that it is clearly different from the one obtained in the 1970 to 1990 period. So now we'll go over how we can model this transition dynamic. So again, we introduce a dynamic matrix called Z, and Z into Mn minus 1 is equal to Mn. So the Z matrix accounts for the dynamism or upward change in transition matrix. If we multiply Z with the transition matrix of a current time, it will give us the transition matrix of the next 20-year period. Right. So our final model becomes uh, pi of from 1 to n minus 1 into p1 is equal to pk. That is m1 into m2 till mn minus 1 into p1 will give us pn. Instead of the previous model which has assumed a constant transition matrix, that is t power k minus 1 into p1 is equal to pk. So coming to the summary and conclusion part, if we use the 2050, if we use our evolution based model to predict the world economic distribution in 2050, our evolution based matrix shows that the world economy will not diverge and will reach and will be heading towards a stable equilibrium in which the disparity between tier 1 and tier 6 countries is far less than what is predicted by a single a constant matrix assumption model. So to summarize or go over our final model, we construct a Markov chain based model using transition matrices that account for the evolution of the world economic distribution, and the matrix